Okay, example 16.17 is an extension of 1612, in which we have a piston that's constrained to move up and down, and they give us an omega about this crankshaft AB right here. Now they want to know what is the velocity, or sorry, what is the acceleration of point C? Acceleration, we don't know. We'll find it. We used geometry to find instantaneous centers, which allowed us to find omega BC. So I'm going to go ahead and write down, we're going to need this. Omega BC was 2.425 radians per second, and omega AB was given to us as 10 radians per second. Alright, the other piece of information we're going to need next is, let's make a position vector for B. So I went ahead and drew the triangle. It was 0.75 in this direction, 0.25. We had an angle of 45 degrees given to us here, meaning that this is 45. So B is located from this point of rotation, a 0.25 times the cosine of 90 plus 45, or 135 in the I direction, plus 0.25 sine of 135 in the J direction. And that is in feet. Let's go ahead and make a position vector for C with respect to B also. I'm going to have a 0.75 cosine, and in this case we're looking at the 13.6. If this is 13.6, as we found before, alternate interior angles tell us this is 13.6 also. That being 13.6 means we can flip the components around and say 0.75 sine of 13.6. That'll be our I component. We could have used cosine and 90 minus 13.6 also for the I component. And we have 0.75 times the cosine of 13.6 for our J component. Alright, using those, let's look at the acceleration of point B. We're going to take alpha of AB and cross it into R of B. And then we need omega AB squared in the direction opposite of R. We get a negative 20K crossed. Alpha is given to us as 20. We needed one of them, so it's given to us as 20 radians per second squared, alpha AB. So we have that it is 20, but it's going clockwise, so I gave it a negative, and it is in the K direction. We're going to cross that into R of B, which is 0.25 cosine 135 in the I, plus 0.25 sine 135 in the J. Alright, doing so, we can find we have a X component of 21.21 and a Y component of negative 14.14. And it's an acceleration, so it's feet per second squared. Alright, that gives us B, but we need the acceleration of C, so let's look at what they call the connecting rod, BC. Alright, the acceleration of C now is going to be whatever the acceleration of b is plus alpha bc. We do not know this. This will be something we find out in our system of equations. We would need alpha crossed into r of c with respect to b minus omega squared r of c with respect to b. Alright, just going to go ahead and give the acceleration at c components in the I and j direction. Just assume that we have them. Let's take a look at the picture. Actually, in this case, we can cross out that it has to be in the y direction or j direction only. So we get to cross one out. Always take a look at your geometry. Okay, and we found the acceleration of b was 21.21 I minus 14.14 j. If we do alpha, we're not even, alpha bc, we'll just give it a positive k direction for now, and we're going to cross that into this vector right here, 0.75 sine 13.6, 0.75 sine 13.6 in the I plus 0.75 cosine of 13.6 in the j. Alright, we also need the minus omega squared we found out omega squared of bc in the previous problem was 2.43. Don't forget to square it, and we want the same position vector, 0.75 sine of 13.6 in the I direction plus 0.7 cosine 13.6 in the j direction. Alright, that's all one big thing right here. So liking components in the I direction, we're going to get 0. There's nothing on the left hand side, is equal to 20.17 minus 0.729 alpha bc. We don't know this, so we need one more equation, or we can find this now. And we really just needed to equate the components in the j to figure out what a of c is. It is a 13.5 feet per second, and it comes out to be negative. That's because even though the piston is moving up, it is slowing down. So the velocity is positive, the acceleration is negative. And alpha bc, if you wanted to know, is 27.7 radians per second squared. And that's also got a squared. Thank you.